SwayamPrabha. Digital India. Educated India.
So, we stopped at looking at the material derivative last time. So, let us sort of dwell on that a little more, okay, and let us kind of look at the Eulerian view, the Lagrangian view, and in terms of how we shall calculate, the change in a physical property of the fluid, So, depending on how I am looking at it, will decide how the derivative will look like, to put it simply. Okay. So, let us sort of take very sort of simple an example just to sort of understand what I mean by that. Okay. So, let us take this flow field. Okay. So, let us say, okay, so this is the time on the x axis and this is the, say, x location, okay, and we have a path, okay, we have drawn, say, a path like that, right. So, this is the path of a particular particle, okay, this is the path of a fluid particle. Okay. Now, let us sort of take that particle, okay, that particle, and say at a certain location, yeah, the particle is here, okay, and at another location the particle is, say, here. This is a particle, okay. So, what I mean is that right. So, since I am talking about a particle, right. So, I am going to just label these write the following the corresponding properties with a subscript star. Okay. So, let us just say this is x1 star. So, the star essentially represents that I am representing the location of a particle of fluid. Okay. And again this one is, say, at time t naught. Okay. So, similarly this one, this location, sorry, that should be a straight line. So, that is actually, say, x2 that, and this is say t1. Okay, this is the time t1. Okay. So, we have something sort of like this. Okay. And let us also label this location as, say, A and this location as B. Okay. So, essentially what we are saying is that at time t naught and a location x1 star, there is a particle and I am calling that location as A. That same particle at another time instant, which is t1, which is t1, right, which is at the location x2, is present at the location which I mark by B. Okay. This is what it is, right. Now, so let us say what is the change. So, now my question is, this is a particle is moving from A to B, right. So, in the Lagrangian view, right, I am following a Lagrangian view, right, which basically is when I follow a particle. So, in a Lagrangian view, okay, Okay, so in a Lagrangian view, right, when the particle is following this path, what is the change in the velocity, so say density. Okay, so what is the change in the density? How would you think you could write that? Okay, so let the particle of the density, velocity, temperature, viscosity, etc., all physical properties of this particle be denoted by with a star. Okay, so if I were to say this, then clearly what is the density of the particle? So the density of the particle at A is, say, so here the density is going to be, I am going to just write that. Okay, so the density of the particle at here is what? You could say rho A denoted by this, right, and here it is rho B star, possible, right. So therefore, if I were to just say the density of an arbitrary particle anywhere, so I am going to just write that as, say, this, right. And how would you find the rate of change of density, rate of change of this density, right. So I would just do this in the Lagrangian view. Does that make sense? So the star itself is basically telling me that, okay, so then density of this density is essentially something like this, rho A star or rho B star. So essentially what I am saying is, so this could be, so in principle here, so density is what in Lagrangian view, so therefore this is actually the rate of change, right, of density, right, which I am writing like this. So essentially I could, I could write this as, so in this, for this particular case I could basically write this as rho star, right, right. The only thing to note here is that essentially this rho star is the density of a fluid particle. We are following a particle. So that is how, so this is essentially the Lagrangian view, right, how I look at this change. So also another way to look at this is when somebody says, what is the rate of change of density? So I think the first question you need to ask is, how are you looking at it? What is your reference frame? Right. So if it is a Lagrangian view, which means then I am focusing my attention on a particular fluid particle, and then I calculate my densities in this fashion, right. So here what you see is a partial derivative, right. So now I am talking about the del here, right, these dels. Okay. So this is a partial derivative. So what I have done here is I said, so this is the Lagrangian view, Lagrangian concept. So the change in the density, so this could be anything, it could be velocity, it could be temperature, viscosity, etc. Right. So this is the Lagrangian view. So at this point, so how is this going to be different? If I take a Eulerian view, instead of following a particle, if I look at if I look at the domain as a whole, right. So then that is the Eulerian view, right, and in that case how will this definition change? What sort of a derivative would I use? Because I am talking about a rate of change of the properties, right. So how will that change, right? Okay. So if I do that, so let us say now, okay, so let us look at that. Okay, let us look at that. So let me be on this screen itself. Okay, so this is now the Eulerian description. Okay, now So the Eulerian view basically is that it comes from the fluid as a continuum concept, right? That's what we said. So essentially we are looking at, you know, several particles, and we are looking at a large domain of the size of the domain is decided such that I can actually divide, I can actually sum up, I can sum up the physical property that we are looking at, in this case density, and take that as one particular value, an average value of that, right. So that is what we have said. So let us say that we are now, the fluid particle here is moving from one domain to the other. Okay. So in this view here, so but I am not looking at a particle, but I am looking at the domains, but these are large enough, the spacing between these two domains is large enough, so that density is not constant between the two, right. Density is changing, but when it moves from one domain to the other, within that domain I use the continuum approach, so that there is a particular density. Okay. Now, how that domain, you would decide on the domain and what is the size of the domain, that will depend on the problem that we are doing. Okay. And I think it is problem specific, so we will sort of, you know, see as we go along. Okay. But from an Eulerian point of view, the point is that we are not looking at individual particles. The only thing is that here also, when we are looking at density, we are not looking at individual particles, but we are looking at a domain size where we can take, following the continuum approach, we can take an average value of that density, any physical property for that matter, to be a singular value on that domain, right. So that is exactly the Eulerian view. From that view, let us say now we regard this location as A, right, and let the density there be rho and the velocity be v. Okay. So say density at A, right, and velocity at A is v. Okay. So now at the way it moves, right. So therefore, as it moves from say location A to location B, right, from the Eulerian view, what is the total change in velocity? What is the total change in that density, right. So the total change in density is, okay, let me sort of write this down. Okay. Total change in density at location B, right. Total change in density at location B. Okay. So this is local change in density at location B, right, plus the change due to the particle moving from A to B with a velocity v, right, plus change, no, not, sorry, I use the word particle, sorry. So local change in density at location B plus change as fluid moves from A to B with velocity v. Okay, just write that like that, with v, right. Does that make sense? So therefore, how do I write this? So the total change in density here is going to be local change in density at location B. So when I said density at A, right, is equal to rho, right, and velocity at A is v, when I wrote this here, right, velocity and density, when I wrote that there, I think what would you suggest I should have also written along with this, to make it a more generic? What I should have done is also written this to be x and t. So what this essentially means is that I am deciding, so in that case let us scratch that out, this. So this is now basically telling me that in the Eulerian view, at a particular location, at any particular location of x and t, in this case we have an x field, so x and t, we have a corresponding density and velocity, right. So this may or may not change depending on how far you are moving, right. It might be possible that if you are moving in x so much that there is actually no change in density, you can see that, right, and we do that too, and velocity also, if you are moving from one location to the other, it is possible that there is no change in the velocity, right, that is totally possible. In this case, if we assume, if we assume that there is a change, how will that change look like in terms of derivatives, right. So that is what we are trying to look at. So therefore, if I have to figure out what is the local change in density at location B in this case, so I am going to just say that it is del rho del t, that is the local change in location B, right. But we also take the change in the fluid because it changes in distance, but at what rate? At this rate, because this is at the rate at which it is travelling. Now, so this is essentially the total change, we spoke about this, and this is what we write as the material derivative, right. So what we are essentially looking at now is the change in a physical property, in this case being density, right, in Eulerian view, in Lagrangian view, and what sort of derivatives are we looking at, right. We are looking at partial derivatives in both cases, but in a slightly different way, right. So there is a difference between the star rho star that I am using here and the rho that I am using here, and you can see that, right. So when I say rho here, rho star in the Lagrangian view, I am looking at rho a star, this thing, which is basically that which pertains to a particle which is located at A, right. Whereas when I say rho x t, this is the Eulerian view, I am basically saying this could be of the density anywhere in the flow field, define it anywhere in the flow field, right. And it is possible that in this sort of a domain, say in this domain, there is actually no change in that density, it is actually one value. So if you do calculate total change in density, if it moves say from A here to B here, you will find that the density change is minimal, okay, insignificant, and so on and so forth. Okay. So that is, so therefore this is the total derivative that we spoke about in the last class. So this is it is represented del rho del t. Okay. Now just look at I will just speak on this for a little while more and then we will stop. So now you see this term, okay. So I think I could take a easier sort of a term, to describe that. Okay, no problem, we can do that here also. Fine. So this is, what is the dimension of this? What I am trying to get at is what is it, because this dimension and this dimension of the two terms should match, otherwise I am putting these two terms together. So in the sense that you understand this, right, local change in density at location B, right. So what am I saying physically, what does this term mean? So there is a change in the density as I move in x, right, but at what rate? That is the velocity which decides that, right. So now what is the units of this first term, right. So it is kg per meter cube per second, is that right? Now here what is this? Del rho del x is kg per meter cube per meter, and velocity is meter per second. So therefore the total, that is why I said del rho del x, which is kg per meter cube per meter, right. So the change in density per unit change in length. So, that is your del rho del x, right, and how fast does this change happen. So, this del rho del x, that will be given by the velocity, and when you sort of combine the two is basically giving you the total change. It has the same units as del rho del t. So, that is also actually the total change in time, in this time, but then this change is due to the change of location, right, and this first term basically represents the entire change during the instant of time, right. Of course, here delta t tends to by definition it's a very small value. Okay. So that is essentially your Eulerian view and Lagrangian view. I could sort of, so we could go ahead and yeah, so look at one more example of this. Okay. I think we should do that. Okay, we should do that, and then we'll close today. Okay, so having said that, let us look at another example, right. Okay, so let us say I have a domain. Okay, I have a domain which looks like this. Oh. Okay, this is my domain. Of fluid flow. Okay. Now, okay, that's a candle. That's lukewarm water. Okay. That is water at room temperature. And this is actually a bucket of ice. Okay. So, now I am going to call these locations, right. This is x1, t1. Okay. Let me, okay, x1, t1, let me first draw an axis system, right, which is essentially like this. Okay. So, then this one is at location x2, t2, this is x3, t3, and t4. Okay. So, as you can see, basically I have these things here. Okay. So, I am going to call this, so let us just say this is O, right, or let us just write this here. So, this is O, this is A, this is B, and this is C. Okay. And let us just say the temperature, right, which I am going to write with capital T. So, the temperature, okay, is T1, T2, T3, T4 at these locations. I have this temperature at these locations. Okay. Okay. So, essentially this is a candle, okay, there is a candle, A is let me write here. So, O is a candle, A is lukewarm water, B is water at room temperature. And C is a ice bucket. Okay. So, now what I do is I insert my finger. I insert my finger in there, right? And I move that finger, quickly across the candle. You know what you will feel there? You feel that tinge of heat instantly, right? So, I will just so like move my swipe it across the candle flame, right, and I will feel that instantaneous heat. So, that change in temperature would be, what would be the change in temperature? So, I said the temperature here is T1, okay, let's say my temperature here is T1. So, that change in temperature is going to be, so I am going to write that here, that the local change of temperature, right, is, so I write it here, local instantaneous temperature, right, is equal to this, right. And now, like we did in the previous case, it moves say to location A, right. Then what should be, there should be another change in that temperature. What should be that change? That change in temperature, now it moves to location say A. My finger moves to the next location say A, right, which has a lukewarm water, right. I move there, right, and I thrust my finger into this tank of lukewarm water. There is going to be a change, right, in that this thing, right. So, what will be that change, right? So, what is going to be that change? So, if I go there, so then so initially I had my temperature which was T1, right, and now the temperature here is T2, right, but the temperature changes, right. So, I have a temperature which is T2, but this was, how is this related to T1, my same finger, right. How is it related to the same finger? Well, T1, so that was a local change, right, here, plus, right, it moves through say distance x, right. So, there is a change because the temperature is moving through x, right, but at what rate? Let us just say u naught, right, u naught. So, then if that is the total change, right, if I come here and then with this change, so initially I was at T1, right, initially I was at T1, the temperature there, the temp was there, my finger, initially my finger's temperature was T1, right, and then I moved my finger through the candle, due to which there was an instantaneous change, right. And then I moved to another location, which is A, due to which I had a change in temperature, which is due to the movement in x direction in space. So, therefore, del T del x, and this was happening at a speed which is u naught. What is u naught? U naught is essentially the speed at which heat is transferring, right. It is the velocity of heat flow. So, that is important to write, isn't it? What is u naught? So, u naught is essentially the velocity of heat flow, and this is velocity of heat flow, say at O. This is at O, isn't it? So, and I am saying that this, the velocity of heat flow, that is not, I mean I am taking the same velocity of heat flow which is at location O, right. So, let me repeat that. So, what I do is I take my finger which is at location at O, right. So, then it basically has the temperature T1, right. So, I bring my finger in, right, which is at the location O, it has a temperature T1, right. So, next thing I do is I move my finger through the candle. I move my finger through the candle, due to which there is an instantaneous change in the in the temperature, which is this, which is delta T1 delta T, right. And then I take my finger and move it to the location A. So, I move it to the location A, right. So, due to which, and then what I do is I plunge it into this change, I plunge it into the lukewarm tank of lukewarm water. So, the moment I do that, there is again another change, because there is a change in x, right, and the change in x is delta T x, right. I take x and it is happening at the rate u naught. So, u naught is the velocity of heat flow, right, which is velocity of heat flow at O, right. So, therefore, so the temperature T2 is essentially now T1, right. So, T1, which what I had originally, to that I did an instantaneous change because I moved my finger through the candle, and then I moved in space, because of which I moved my finger through the space, because of which there is a change in, that is, I move my finger through the control volume, the density at a rate u naught, and velocity of heat flow at O, right. So, this velocity of, so you can see here there is a change in this heat. So, this heat transfer is basically between my hand and the atmosphere around it, right. And when again, so when I, so this is at T2, right. So, therefore, I can essentially, so now if you see this term now, if you look at this term now here, this one, if you look at this term, this is essentially nothing but the total derivative, right, of the temperature at, okay. So, this is T1 again, sorry about that, okay. So, then therefore, this is nothing but, so this thing is nothing but, right. So, this is essentially dT1, the total change in the temperature T1 as it moves from location O to A, right. So, essentially this is total change in T1 as it moves from O to A. Is that right? Okay. Right. So, therefore, I can just write that T2, okay. So, therefore, now I have a new temperature which is T2, right, which is T2, and this is equal to nothing but T1 plus dT1 dt, right. So, now this is it, Okay. Now again, now what I will do is, so now again what I will do is I will move to location B. Now before I move to location B, what I will do is I will plunge my finger, which is currently at temperature T2, right, and I will plunge my finger, right, into the tank of lukewarm water at A, right. So therefore there is going to be an instantaneous change, right, in my temperature, which is T2, right. And what will that change be? So that change, so now that, so this is okay. Now let's sort of do that. So this is something I have. Okay. Okay. So this is the first step. Okay, the next step again, so what I am doing is, again I am plunging my finger, right. I plunge the finger into the tank here, into the tank of lukewarm water, right, so that there is an instantaneous change in my temperature, which is delta T2 T, right, and then I move to location B. If I move to location B, so then what is the change there? It is delta T2 delta X, and let us just say the velocity of heat flow is UA. Is that right? Okay. So that is a total change now. Okay. So then again, so therefore now I have a new temperature, right. I have a new temperature at location B, right. So therefore, which is the T3 is essentially T2, the temperature was T2, to that this change has been added, right. So this change again is nothing but, so this change is nothing but again T2 plus d T2 dt. Right. So henceforth, so again what I do is, so I am going to just write the whole thing. So then again what I do is I move, now I am at location 3, right. I am at location 3. So what I now do is, my finger is now at a temperature which is, I have moved to temperature here at T3. My temperature is T3 now. So I have gained T3 temperature, and now what I do is, again I plunge it into the room temperature. I plunge it in the tank of room temperature. So therefore there is an instantaneous change in my temperature, right, which is del T3 del T, and then again I move to another location which is C, right. So therefore my okay, so let me write that down. Okay, so there is an instantaneous change in my temperature, and then again I move through X with, say, uniform velocity of heat flow, which is this, right. So that is my change in temperature, right. So now I am at the location C, right. So which is essentially this. So now the temperature here is what it was, so T3 and plus the change in the temperature, right. So so essentially T4 is equal to T3 plus dT3 dt. So essentially what I am saying, it's kind of saying that, in this domain, why is there a temperature change at all? Because I am doing these things. So I am doing these things. So essentially it could have been just, if I have just a candle, and then everywhere it could have been T, but there is a change in the temperature, right. It could have been a change. So the change is coming because I am creating some kind of a heat flow, and therefore there is this change, right. So, I am trying to calculate that. Now, all of this when I see here, so when I wrote this down, so where is T1? Okay. So, let me write down the T1 also again. So, essentially here, so therefore, T2 is essentially T1 plus dt1 dt, right. Now, when I do this, right, when I do this, so what exactly, I mean, how am I, so this is like asking you, the reverse kind of a question. So, how exactly am I looking at the flow, right? What is my reference frame, right? So, this reference frame is obviously Eulerian point of view, right, Eulerian view. So, because I am basically saying that I am moving in the domain, right, and there is change in the temperature, right, because there is fluid flow, if there was, so if I didn't have these things, so if I just think, if I had just think about this, okay. Now, say I had this candle, right, and I would move my finger through the candle and there would not be a change in the temperature for some reason, okay, maybe that it's not hot enough or something, okay. So, in that case, so delta T1, delta T would be 0 if there is no change there, and then again when I move, say, instead of this, instead of say the tank with lukewarm water, say I had another candle there, right. So, okay, so and then when I move from say O to A, right, there is actually no heat exchange, there is no heat flow. So, this U naught that we have here, U naught is actually 0. So, then there is no change. So, it is possible that it can move from say location O to location A, and actually there is no change, there is no instantaneous change, neither there is any change, if I move from it. So, but this is an example which I have created just to show that this is how you can create that flow exchange. You could also think of this in terms of say fluid flowing between slopes, right. So, in the sense that I can have a series of steps, right. So, say I have steps like this, say I had steps like this. Right. So, if I dropped say some water right here, and it will just trickle down like this, right. So, then there will be a change in the velocity as I go along into the field, but then if I had the same, then there would not be a change, right. So, then there would not be a change in the velocity. Okay. So, this change of physical property, in this case being the temperature, is happening because there is a fluid flow, because there is the fluid flow. This fluid flow in this case is the heat flow. I am saying this from the concept that when we said that in the continuum approach, right, we will take an average value, right, of the physical property, and that will be the value of the property throughout the domain, right. Is that getting violated here somewhere? That's what I am trying to understand. So, the point is that if you didn't have all these things, if you didn't have a candle and some other 3 different types of sources of heat which were at different temperatures, then it would actually have the same temperature. There would not be any change in temperature. Then on this entire domain, you would actually have the same temperature. So, your continuum approach is fine. There is nothing wrong with that. Okay. Now, also there is nothing wrong with it. This continuum approach is not getting violated. What is happening is, as I move from say as location O to location A to B to C, there is a heat flow, there is a fluid flow, right, because of which that heat is getting transferred. I think that is the key word, heat is getting transferred. right. Of course, it cannot be manufactured, or it cannot just disappear. So, it is getting transferred. Now, because of that, the density is getting a little readjusted in the domain. Okay. So, in that context, so the continuum approach is not violated when I say now that okay, now at different locations I have different physical properties, different values of the physical property, right. That is because it is because of this fluid flow, which is the heat flow, right. Some of the heat is which was here, right, is sort of getting, so the heat which is here, right, it is getting transferred. It is getting transferred to the atmosphere, and therefore, that change is happening, right. So, this is still an Eulerian view, and we still have the Eulerian view with the continuum approach to the fluid flow. So, where am I located here? So, where I am located here is actually here. My axis system is actually somewhere here. I am actually located here. Okay. So, this is my location, and this is essentially my Eulerian approach. This is my Eulerian approach, and I look at the total change, right. So, Eulerian approach in the sense that I am looking at the total change, right, a total change in the temperature, I write here, right. So, when I write this here, so this total change in the temperature as I am moving within the domain, right, as I am moving within the domain, and the total change is and the change is happening because heat is getting transferred. It is just sort of getting a little readjusted between the locations. Okay. So, that is the Eulerian approach. So, therefore, and then you can see that how I write that temperature. So, that temperature basically, so the temperatures are essentially connected to each other. So, like I said, so that is why I write. So, essentially you could have said that everywhere it should have been T1, no, but it is connected because it is moving from when it was a T1 to that there is a change which is this total change, and therefore, it has moved to T2. Right. So, that is how these changes are connected, and hence the temperatures at these locations are connected. Okay. So, if you actually see this, if you actually see these 4 expressions that I have here, right. So, therefore, you can see that okay, I had actually written it here, actually I have this 3 in here. So, yeah. So, therefore, you have T1 this. So, delta T1, delta T, delta T2, delta T, and delta T3, delta T. This is the total, basically total change of the temperature in this domain. Okay. Now, if you had to, so therefore, and then again this is the location. Now, if you had to look at this in a Lagrangian point, in a Lagrangian view, right, where you would just follow a particular particle, then what would it be, right? How would that be? Well, that would be simple, right? So, then that would essentially be that instantaneous. So, I follow one particle, it is here and its local change, right? I follow that particle. So, then what would be my reference frame? Reference frame is essentially here. You can start at say O, right, and then you follow that particle throughout. You follow that particle throughout. Right. So, it essentially that Lagrangian form will be, I will just highlight it here. So, Lagrangian is essentially this one, this, right. So, that will be the delta T1 delta T, then in the Lagrangian view delta T2 delta T local, and then delta T3 that, and what I haven't written is delta T4 delta T, right. So, these are essentially, so this is essentially, so these are the ones that I have highlighted in yellow is essentially the Lagrangian point of view. Okay. All right, so I think we will sort of close here today. Okay, so it is important that we understand this concept, right? Understand the Lagrangian view, the Eulerian view, and the continuum approach, right? So we are talking about a domain, a large domain, like as I have here right now. Okay, does that mean, so if I have if there's a change in the physical property, does that mean I am violating the continuum approach? I think you need to think about that, okay, on those lines, and then review this material that we discussed. Okay, so I think we come back and start slowly discussing what turbulence in this is all about. Okay, so we will begin there in the next class. So we'll stop here for now. Okay, thank you.